Hello everybody and welcome to my talk. I am Anne-Laure Boulesteix, a professor of medical statistics at the LMU Munich Medical School. My talk will give a statistical perspective on the replication crisis that has been described by my colleague Nikolaus Plesnila in the previous talk. More specifically, I will focus on publication bias, HARKing and p-hacking, which can be seen as the statistical issues behind this replication crisis. I will explain these concepts in the context of statistical testing because it's much easier to formalize in this context, but these are actually much more general issues that are not specific to statistical testing. First, let me very briefly introduce statistical testing terminology. In statistical testing, we usually test null hypotheses of the form that there is no difference between groups or no association between parameters, no interesting pattern, to put it simply. Researchers are usually interested in establishing the contrary of the null hypothesis, namely that there is a difference, there is an association, there is an interesting pattern. Unfortunately, statistical tests make errors. They may fail to reject H0 even if H0 is false, which is denoted as type 2 error. This is a very important issue for scientific practice, but we will not focus on this issue in this lecture. In this lecture, I will focus more on the type 1 error, which is directly connected to the problem of fishing for significance and publication bias. A type 1 error is when H0 is true, but the test rejects H0. So this is a false positive result, positive in the sense that the test states that there is something interesting, something positive, but this is false because H0 is actually true, so there is no interesting pattern. Errors in testing are common, not just in statistical testing. Just think of medical tests like mammography for breast cancer screening. H0 would be that there is no breast cancer. H1 would be that the woman has breast cancer, and a medical doctor may make the two types of errors. Type 2 error would be to overlook a breast cancer, and type 1 error would be to diagnose breast cancer even if there is no breast cancer. Now, in statistical testing, the type 1 error is fixed by construction of the statistical test. That is, the statisticians who developed the statistical test developed it in such a way that the type 1 error has a fixed value, alpha, which is chosen by the user. A very common choice is 0.05. Now imagine that we are not conducted only one statistical test, but 100 statistical tests, 100 independent statistical tests of null hypotheses that are in reality true. So they shouldn't be rejected. But because of this type 1 error, some of them turn out to get rejected. On average, when we test 100 independent tests, we expect that 5 of the 100 null hypotheses will be rejected. Will be rejected wrongly, because they should actually not be rejected. So these are 5 false positives on average, false positive results. There are many situations where we perform several tests simultaneously. Just think of the situation where we repeat the statistical test in different subgroups of patients, or when we do tests for different biomarkers, when we test their association with a clinical outcome of interest, and we do that for 100 biomarkers. These are also 100 tests. Or more generally, think of the situation where one tries different variants of the data analysis. So one also does different statistical tests at the end. Another example, which is also very important with respect to publication bias, as we will see later, is the case of several RCTs that address the same research question, for example, whether drug A is better than drug B. Imagine that 100 RCTs are performed to test this hypothesis. Now, on average, we will have 5 of these 100 trials that find that drug A is better than drug B, even if it isn't. Even if the null hypothesis is true, we will have on average 5 false positive results, these green results here. And the 95 red rectangles display the negative results. In our analogy with medical testing, we would say that a doctor who conducts a lot of mammographies on healthy women is likely to eventually get a false positive, exactly as we are likely to get false positives if we are performing a lot of statistical tests. Now I would like to come back to one of the examples I mentioned, 100 variants of data analysis. What I mean here is that when performing a statistical test, we have to make a lot of decisions regarding this test. For example, should we do man-Whitney test or t-test? If we do a t-test with equal variance or not, will we keep outliers or exclude them? Will we exclude a particular subgroup or exclude missing values or impute missing values? There are really a lot of decisions that have to be taken before performing data analysis. And all these decisions can be represented as a sort of tree or as a garden of forking paths or forking p-hacks, following the terminology of Andrew Gellman and Eric Locken. So what they say here is that all these decisions lead to a huge number of possible results, of possible p-values in the case of statistical testing. Now imagine that someone gets this huge number of p-values and select the smallest one, report only the smallest one, and forget all the other. This is the mechanism behind fishing for significance, or p-hacking. In other words, if we test enough times, we finally get something significant. Even if there is actually nothing, we finally get a false positive. Even if there is actually nothing, so we shouldn't find anything significant, but due to this type 1 error that leads to false positives, we finally get something significant. Now, why fishing? I think the analogy with the small fisher is interesting because it allows to better understand this mechanism. Imagine a fisher wants to show that fishes are very big in a particular lake. So he tries to fish at different places, here, here, here. He always fishes small fishes, so he's disappointed. He gets large p-value of small fishes. And look here, by chance, he turns out to get a somewhat bigger fish, or in statistical words, a significant p-value. Well, this would just be chance because fishes are not exactly equally big. This would just be chance, a false positive result, but then our fisher would say, great, I could show that in this lake fishes are very big. Now imagine what happens if he tries to confirm this statement, he tries to validate this statement by trying again in the same place to fish a big fish the following day. Of course, the fish this time will probably not be big again because it was just the result of chance, it was just a false positive. So he's very likely to get a small fish this time. And actually, exactly the same happens to us when we fish for significance when doing statistical analysis and then try to confirm our results in later independent validation studies. We are very likely not to find the same big fish again. This leads to the so-called replication crisis, or at least this is a contribution of the statistical aspects to the replication crisis. Now I would like to come to my second topic, publication bias, which is at first view not related to fishing for significance, but we will see that there are some connections. Studies with significant results have much higher chance of being published, which leads to the so-called publication bias. The literature is biased. This is due to different factors like editorial strategy or influence of reviewers, because both editors and reviewers are more interested, are more impressed by significant results. They are more likely to accept these results for publication. This is also due to something like authors' self-censorship. You know, when authors lose their interest in their study because they see that the results are not significant and this study ends up in the file drawer, this also contributes to the publication bias. So big fishes appear in the newspapers and small fishes go to the bin. This is publication bias. Now let's look at the publication bias in light of the statistical testing theory we have seen at the beginning. Let's come back to our example of drugs A and B that actually have the same effect. And so the null hypothesis that they have the same effect, that there is no difference between drug A and drug B, is true. And we consider 100 clinical trials investigating this question, so comparing the effects. We have seen that we can expect that 5 of these 100 trials will wrongly show a significant effect difference. The problem with publication bias is that these 5 studies that are actually false positives are much more likely to get published than the 95 other which were true negatives, but which were correct. So at the end we have an extremely biased picture of the reality, which may ultimately harm to patients in some cases. If we look at the big rectangle here, which displays all studies that have been performed, we see that, well, the negative studies dominate, the red studies dominate, and there are only these 5 false positives. Now, if we look at what is published in the literature, it may look like this, namely that the false positive results get published because they are positive, because the p-value is significant, but most of the negative results don't get published, well, maybe one or a few are published. So in the literature, we feel that that drug A is better than drug B, that there is something positive. Also, we actually know that it's not true. That was our assumption that drug A and drug B, have the same effect, and that drug A is not better than drug B. So we get an extremely biased picture of the reality. We see this, but the reality was this here. Now I would like to give a very concrete example from the study by Turner and colleagues on antidepressants, in particular paroxetine. Here is a simplified view of the results concerning paroxetine. I decided to focus on the 7 studies that led to a positive FDA decision and the 7 studies that led to a negative FDA decision. They are displayed here. And in the paper by Turner, we can see that 7 of the 7 positive trials were published, but only 2 of the 7 negative trials were published. So this is what has been done, and this is what we see. We see here that the literature gives a very biased picture of what has been done. Now, what is the connection to fishing for significance? So we have seen that a publication bias results from the fact that studies with significant results have much higher chance of being published. We, of course, all know that researchers are under publication pressure. So because of the publication bias, researchers are actually under pressure to obtain significant results. This, of course, leads to a very big temptation to fish for significance. So recall that if we test enough time, we get finally something significant, even if there is actually nothing. That was the fishing for significance process. And now, considering the publication bias, we see that this false positive, this significant result, has higher chance of being published. So the publication bias interacts with fishing for significance at 2 stages. On the one hand, the publication bias encourages people to do fishing for significance to get published. On the other hand, once the people have fished for significance, publication bias kind of amplifies these false positive results. So this is fishing for significance that we have already seen. We have one null hypothesis, and we try different analysis strategies. So we do a lot of tests, and at the end we often get a false positive results out of all these p-values. This was a fishing for significance mechanism that we have just talked about. Now there is a variant of it which is called HARKing, which is something different but strongly related. HARKing stands for hypothesizing after results are known. So in HARKing, there is no priori null hypothesis that is considered. So if the statistician would ask the medical doctor, what is the null hypothesis? He would basically say, well, I don't know, please test all possible hypotheses. We will then see what happens, and we will then see what we publish. We will publish the most significant ones. So both mechanisms are similar in the sense that they generate a large number of p-values. They generate this garden of forking path, and at the end, researchers pick up the most significant p-values out of these many p-values. So this is similar, but the garden of forking paths arises differently in fishing for significance. It arises from the different combinations of data analysis strategies that are being tried, and in HARKing it arises from the different hypotheses that are being tested. But at the end, it's similar. We have a lot of p-values, and the most significant ones are selectively reported. In a few words, to conclude, studies with negative results tend to remain unpublished because of the publication bias, and many negative results are made positive through fishing for significance. On the whole, these mechanisms lead to a large proportion of published results that are actually false positives and that are not replicable. Of course, there are many other components in the replication crisis. Statistical aspects are only one component of this replication crisis, but they are likely to contribute a lot to this replication problem. The good news is that there are partial solutions to this problem. My colleague Xenia Schmalz will talk about registered reports in the next talk. The basic idea of registered reports is that the review process takes place after the study design stage and before data collection and data analysis. So it kind of prevents or reduces the publication bias and the fishing for significance process and HARKing process, as my colleague will explain in her talk. Thanks a lot for your attention. Bye bye.